Welcome back, guys. So in this lecture we will be understanding about the big O notation, its uses. Okay, and before that, before starting with the lecture, I will assume you guys have already installed VS Code in your machine. And what I have done is I've basically created an HTML file and I've connected my JavaScript file with that. Okay, and this is how I'm running my code. And if you don't want to use any code editor, then there is another option as well. Let me show you quickly. You can go into your Chrome's source tab. Okay, and in source, what you can do, you can find an option called snippets. Okay, in snippets, like if you are unable to see this option, you have to click these two arrows, and then here you will find the option for sure. Okay, snippets. So in snippets, what you can do, the way we create JavaScript files and we store it in our machine, same way you can do it in your machine, like in your browser, in your Chrome window. Okay. So what you have to do, you have to just click on this new snippet and then let's say test new snippet. Okay, and hit enter, and it will work the exact same way as it works in our JavaScript code. So let me quickly paste this code here. Let me uncomment it. And then all you need to do is you need to click either this play button or you have to hit the command enter if it is Mac or control plus enter if it is Windows. Okay. So let me quickly show you. See, the moment I clicked, I got the result in the console. Okay. Let me show you with the shortcut as well. See, I'm getting the result as much as I want. Okay. So this is how you can work with the snippets. So this is a nice little feature of Chrome. So you can make use of it if you don't want to do anything in the like VS Code or in your code editor. Then will be the simplest way to write your code along with me. Okay. So let's get back to our topic. So why we need big O notation in the first place, and what do you understand by the performance of the code? Like, is it the code is fast, or it is taking less space, or like it's more human readable? Okay, so what do you understand by code? So we will be understanding all these things in this video. Okay, so let's understand the definition of the big O notation first. Okay, so it is basically tells us like how the runtime of an algorithm will grow as the n grows. Okay, as the input grows. And instead of talking about the exact time and space of an algorithm like is occupying, we talk about the general trends. Okay, I know this definition will sound confusing for you guys, so that is why I've shown you these definitions in the beginning. So you just have to keep in mind, and then when I start explaining these topics, like you will be crystal clear with these definitions. Okay. And now, why we need the big O notation? Okay, is the question. So it helps us to calculate the performance of an algorithm to pick the better solution for our problem. So let's say you went into an interview. Okay, he gave you a question and he asked you to solve it in 2-3 different ways. Okay, because he wanted to see you like which better approach you can use to solve that problem. Okay, what are the better approaches you can use? Okay, you have a same problem, but you have to write 2-3 different solutions of it, right? So they just judge whether you are able to write the performant code or not. Okay, and how they does that? With the help of big O notations. They do it. Okay, so we have two examples here. Okay, so what these examples are doing, basically these are the functions where we have to pass some number, and then they will give us the sum of that number. Let's say I have passed 3. Okay, so it will give me like 6, because 3 plus 2 plus 1. Okay, this way it will sum the number. So let's pass 3 and it will give me 6. And let me show you 3 plus 2 plus 1, it is 6 only. Okay, now let's pass another number, let's say 12. Okay, so it is giving me 78. Let's pass 10. Okay, and it's giving me 55. Okay, so this way, let's quickly check the other function as well, whether it is working fine or not. And 2. Okay, so it is also giving me 55, the same result what I want. Okay, so now let me show you what is the difference between these two functions. Okay, so this one is using a for loop. Okay, and this one does not use any for loop. It does not even use any variable inside the function, but this one does. It is using few variables and it is using few operators in it. Okay, and we are passing some input in this function, and based on that input we are we are processing our code, and then we are returning some output. Okay, same thing we are doing here. We are passing some input, and then based on that input we are doing some calculations, and then we are returning the result. Okay, so right now we will track the time, like how much time these two functions are occupying. Okay, these two functions are taking to run their code. Okay, so for that you can use the JavaScript's built-in performance.now. So I'll take these ones, I'll put them here, performance.now, and I'll pick this whole thing here. Okay, so now what I'm doing is I'll capture one time in this t1 variable. I'll capture another time after this code's execution in the t2 variable. Okay, and then I'll subtract them, and then I'll divide them by 1000. Why I'm doing so? Because I want to convert these times in the seconds. Okay, if you don't divide it by 1000, then it will give you time in milliseconds. Okay, so this thing you have to keep in mind. Now let's run the same code again. Okay, so this time I got 0.029 seconds. Okay, for this code to run. Let's refresh it again, and this time I got 0.04 seconds. 004 seconds. Okay, so let's run it again. This time I got 0.002 seconds. Okay, let's run it again. This time 0.03 seconds. And if you notice, like, I'm not even changing any single line of code here, right? But the time is still getting changed. So that means we cannot track the performance of a code by its time, because the timing depends upon machine to machine, right? It doesn't matter like which machine you are in. Like, it will give you the different time of the exact same code if you're trying to run it multiple times, right? As we are seeing here. So let me refresh it again. Again I got 0.03 seconds, and this time 0.032 seconds. Okay, so every time it is changing only, right? Now let's quickly see that for the other algorithm which we have wrote, or the function which we have wrote. Yeah, so here comes the fun part actually. Okay, so this time the code took 0.007 seconds something. Okay, and let's refresh it to see few more results. Okay, so this time also 0007, but this time it's changing in very minor, very fractions of milliseconds. See, it is still 0.0007, but in some minor milliseconds it is changing only. Okay, 0.0008 and some minor milliseconds. Okay, it is not changing like 0.003, 0.002. It is changing here only in this portion. That means it clearly says like this code is a little bit faster than this one, right? Let me uncomment these two things again to show you the clear results. Okay, let's name them T3 and T4 because they are like overlapping each other right now. T3, oh sorry, it's T4 and then T3. Okay, so as you can see, what is the difference? The first one took 0.0042 seconds. Okay, let's consider this part, 0042 seconds. But this function took like 0007 seconds, right? That means this one is way faster than this one. Okay, because here we are using a loop and here we are not using any loop. We are just directly returning, we are doing some mathematical calculations and we are returning the result. Okay, we are not putting any for loop or any extra variable. Okay, so yeah, tracking by time is, for the small codes it is totally fine. Like for small codes, that time complexity doesn't even matter, right? Whichever solution you provide, that is a better solution. Okay, but when you are working with the large code base, when you are working with the large data sets, okay, so let's say you're planning to work in Google or any other company. Okay, there the performance does matter, because there you have to deal with millions of, thousands and millions of data sets. Okay, and one algorithm, if you write one algorithm that is like performant, that can save hours of time, right? So let's say you have executed a code, let's say you have executed a function. Okay, it took just half an hour. Okay, I said a lot time. So let's say it took just 3-4 seconds to execute. Okay, to return the result of millions of data. Okay, that will save an hour of time instead of running a simple for loop or some code where you are not caring about the performance at all. Okay, where you are not caring about the time complexities at all. So when you are working with the large data sets, time performance and let's say time complexity and space complexity does matter a lot. Okay, so here let's understand what happened. So here we have passed n, right? So n is our input. So if we are passing n, is it affecting anything here? So we have seen, like with the help of performance we can track the exact time, right? But how we will express it, whether it is a good code or a bad code, okay, we basically can't express, right? Because we won't even remember the numbers, like how much milliseconds this code took to execute, right? So that is why we talk about the general trends, like what will be the time complexity of this particular code, how much time this code will take, and how we will calculate that. We calculate based on the number of operations that particular code is performing. Okay, and how it is getting affected by the input size. Okay, so let's say I have passed 3 here. So does that 3 affecting this for loop, is the question. So if you are passing 3, then this for loop will run 3 times. Okay, and if this for loop runs 3 times, then that means this plus an assignment operator, it will also run for 3 more times, right? This increment operator will also run for 3 more times, right? And this one will also run for 3 more times, right? This one is constant because this will run only once, and this will also run only once because this is outside the for loop. Okay, so here the um, input size is affecting our code. So if we are passing 1000, then this for loop will run for 1000 iterations. Okay, so that means there will be 1000 operations, there will be 1000 additions, there will be 1000 um, assignments into a variable, right? There will be 1000 comparisons and 1000 incremental operations, right? So this way, in fuzzy trend, we say like this code will take O of n time complexity. Okay, so the time complexity of this code will be big O of n. Okay, because here this n, basically it is like O of function. Okay, where we just care about the input. So that is why we write it like O of n. Okay, we are checking the big O of the n. N is the input. Okay, we won't consider the function, we just worry about the input. If the input size grows, does that affect our code or not? Okay, so right now the input is directly proportionate to our code, because changing its size is changing like it's basically increasing the operations, is increasing the number of work this code has to do, right? So the time complexity of this code will be, let me write it down quickly. So time complexity of this code will be O of n, because this will be running n number of times. N can be 0 to infinity, minus infinity to plus infinity. Okay, that's why we take a general term n, right? Yeah, so now let's move to this code and then let's analyze like what's happening in this code. Okay, so in this code, like we are passing n, right? N is our input, as you know by now. So if you pass 10,000, million, 2 million, or any number, okay, minus infinity to plus infinity, is it affecting our code or not? Okay, so whatever value we have in n is not affecting at all, because we will still have only three operations here. Okay, this division, addition, and multiplication, right? So if you pass 1000, then also it will be like 1000 into 1000 plus 1 divided by 2. If you pass 10,000, then it will be like 10,000 into 10,000 plus 1 by 2. So the number of operations won't change. So that means it is, we say in general terms, it is constant time. So the O of n is not affecting the performance of the code. So the time complexity for this one, let me quickly copy. Time complexity for this one will be O of 1. And 1 means constant time, right? So this way we calculate the time complexity of an algorithm, okay, based on the number of operations that code is performing, and are those operations getting affected by the size of the input or not? Okay, apologize. Yeah. So if the number of if the size of input is affecting the code, or if it is like increasing the number of operations in your code, then the time complexity will be according to your code, right? So since we have only one for loop, it will run for n iterations. That is why we have O of n. Okay, and let me show you like how we got O of n. So let's say this plus operator will run for O of n times, right? We have wrote already O of n, and then let's just write it parallelly. Yeah. So this plus operator ran for O of n times. Okay. And then this assignment operator ran for O of n times. Okay. And then what we have these comparison operators. Okay. This also ran for O of n time. Obviously it will run for O of n time, because if you pass 5, then it will compare 5 times, right? So yeah, now we have incremental operator, which is shorthand of plus 1. Okay, so it will also run for O of n time. Okay, so this one, this one, this one, this one, we have 4 O of n. Okay, or comparison n equals to plus, have I missed something here? I guess no. 1 2 3 4. Yeah, now this operator will run only for one time, right? Because this is not inside any for loop, so it will run for just once. Okay, and this one will also run for once. This one will also run once only, because in initial loop it will just set the value of the I, right? So this operator will also run once. Okay, so let's remove it. Let's keep it simple. So we have 1 2 3 4 4 O of n, 4 O of n plus 1, right? Because we have constant operators as well, constant assignments, like which are running only once, and then 4 O of n's which are running n number of times. So we won't write like this, right? We won't sum up everything like how many n's are running in this and we write it, right? So in general terms, how we write it, we simply remove the constants from it. Okay, and we simply write this piece of code. So it will become like this after removing all the constants, right? So all these things end of the day are running for n number of times, right? So it doesn't make sense like if you are summing them and then you are writing them like this. Okay. So short and simple, you will write just O of n. It's not 40 of n, it's O of n. Okay. Because this loop is running for n number of times. Okay. So that is why it will be O of n. And yeah. So here time complexity is O of 1. Why it is O of 1? Okay. Because here you are passing an input which is not even affecting any operator here. Okay. Operators will be 3 every time. Okay. Whenever you run this code. So that means we can say like operators are 3 operators are constant. And for constant we write 1. Okay. If the operators constant we write 1. Okay. So that is why O of 1 we use for the constant time complexity. Okay. So it is known as the one of the best time complexity in terms of code. But most of the time like we, we we have to write the code which takes like O of n or O of n square as well. Okay. Because it depends upon the situation and the problem statement which we are working on. Right. Okay. So now I think you have got the at least some idea like what is O of n and how we calculate the time complexity. Okay. And how we write it down in terms of big O notation. Okay. So let's understand like what is actually big O. Let's get back to our definition again. So it basically tells us how the runtime of an algorithm will grow as the input grows, right? So I think by now you understand this definition better. So you are passing some input into a function, okay? And if your code is getting affected by the size of that input, so that is what we basically calculate, okay? Instead of talking about the exact time and space of an algorithm is occupying, we talk about general trends, right? Because see, like if you are telling to someone like how this code is performing in terms of exact time or exact space, you can't explain them well, right? But you explain them in terms of big O notation, like this code is taking O of n, O of n square, or like O of 1, then they will quickly catch like what is the performance of that code. Okay. So that is why we talk in general trends. Okay. Because I've already shown you guys like I was running the same code multiple times in my machine and it was giving me different outputs even for the same code. Okay. So we cannot rely on the time. We cannot like track time manually and we can tell someone like this particular code is going to take this much time. Okay. Because it doesn't matter like which machine you are on and like what is the processor of your machine, the times may differ every time. Okay. And it also depends upon the situation or like mood your computer your machine is on that day. Okay. So that is why we talk about the general trends. We calculate the number of operators in the code and then we identify whether they are getting affected by the input passed to the function. And if so, then we calculate the time complexity based on the number of operators in that function. Okay. So yeah, this is time complexity in a nutshell for these two things. And I have few more things to show you guys. Like let me quickly show them. So I've shown you the time complexity of just one for loop, right? What if you have two for loops parallelly? So what will be the time complexity here? Okay. So here also like if you are passing n, okay? So this code is taking O of n. You are sure by now, right? O of n, this will be taken. Okay. And you have again a for loop. So this is also going to take O of n only, right? Right. So if you sum them, then what will happen? It will become 2 big O of n, right? And what I have said, we remove the constants from the big O notation. So again, it will become O of n only. It doesn't matter how many for loops you have, until or unless the for loop is inside of for loop. Like if the for loops are at same level, then the time complexity will be always O of n only, right? But if the for loop is inside of this for loop, okay, then there is something to worry about, right? Because this for loop will run for n times, but it will run for n times in every iteration of this for loop, right? So we have O of n here, and I know guys this is getting a little bit mathy, because if you're learning about data structures and algorithms, you have to be aware of at least some basic maths, right? And I hope you guys are aware of the maths. And if you're not, like, I'll make you comfortable here, right? You don't have to worry. We'll learn everything gradually. So no issues. Why it's not going? Okay. So let it be. Yeah. So we have two for loops here. So how it will run, let's understand. So let's say we have passed 3 in this. Okay. Let's say we have passed 3. So this whole for loop will run for 3 times, right? And since this number is directly proportionate to this loop, it will affect our this loop as well, right? This loop will also run 3 times, but in these 3 for loops. So if the first loop is running for 1 time, then inside of this loop will run for 3 times, right? Like 1 1 1. Okay. And then in the second iteration, again it will run for 3 times, right? And again in the third iteration, it will run for 3 times. So this way we have O of n of this and O of n of this. So this O, the outer O of n, will get multiplied with this O of n. Okay. This way. And this one will become big O of n square. Okay. So this 2 should be here, but in VS Code, like, I have no idea like how we can make it as a square. So anyways, so you have to consider this as a square. Okay. So it will be O of n square, right? Because the input which you are passing, the time will be increased quadratically, right? If you are passing 2, earlier it was taking, let's say, 2 seconds. Now it will take 4 seconds. Okay. Because it have multiple operations. The number of operations are getting almost double or quadratic, right? For every size of the input you pass, if you are passing 10, then this operation will perform 10 operations, like this for loop will perform 10 operations. Okay. And then inside of these 10 loops, it will also perform 10 extra loops, right? Which will have some 10 extra operations. So this way it will increase in quadratic way. Okay. So the time complexity of this nested for loop will be O of n square. Okay. If there is another for loop inside of this for loop, then you simply have to multiply it like so, and then you have to see what will be the time complexity of it. Okay. So quick summary, like, if your value is not affecting the number of operations in the code, then the time complexity will be O of n. If your value is affecting the number of operations in the code, and if it's just one for loop, it's just one loop which is running for n times, then time complexity will be O of n. And if there is 2 nested for loops, then time complexity will be O of n square. Okay. And if the for loops are at same level, like this one and this one, then time complexity will be still O of n. Okay. And why is that so? Because we don't consider the constants in it. Okay. So yeah, this is all I wanted to tell you guys about the O of n. And this thing I have already covered, like we pass basically the function, and we only care about the input size in it. Okay, so that is why we write like O of n, because we only worry about the size of the input which is passed to a function. So this is a function, and here n is an input. Okay, so like we just omit this thing, and then we write just O of n. So based on that input, what should be the time like that algorithm is occupying. Okay, so this thing we have already seen, like we check the number of operations performed in a code, and is it getting affected by the size of the input or not. Okay, this is what we used to do. This is basically a fuzzy trend we used to follow. Okay, because it doesn't matter like which machine you are using, right? The operators will be same, right? Operators won't change. Okay, so we consider the operators instead of the time. Okay, if the interviewer asks like we can track the time with the help of performance.now, or we can track with some other time tracker manually, then you can explain them easily, right? Like even for the same code, the engine, like your machine can show you like different times. Okay, it can occupy like different times um, on every running of code, you can say, every time you run that code, right? So every time it may differ, so we cannot rely on the time we track manually, and it is not at all optimal if you are working on a large code base, right? For smaller functions you can track the time manually, that is totally fine, but for the larger code base it is not at all acceptable, right? So that is why we use the fuzzy trend, which is called big O notation, where we basically calculate the number of operators, like how many numbers of operators are being used in that particular algorithm, and how they are getting affected by the size of the input which is passed to the function. Okay, so yeah, this is it for this lecture, guys. In next lecture we'll be talking about the space complexity, because here we have seen already the time complexity. We will be learning about the space complexity right in the next lecture. So till then, happy coding.